Hello AP Chemistry and welcome to 16.7 weak bases. So, first of all, it's important to note what a weak base is, right? So, like all bases we've talked about, right, it has to have a lone pair, right? Otherwise it can't function as a base. So it must have a lone pair. Now, if we think about what that means, right, again, going back to what we talked about in chapter 4, one of the most common ones are going to be amines, right, where that is a nitrogen stuck to three things, and because nitrogens have 5 electrons in their valence shell, if they're stuck to three things, typically that means there's a lone pair, right, which means that's one of our most common weak bases. Another way to think about weak bases, going back to stuff we've already talked about at the beginning of the unit, our weak bases are going to be our conjugate, the conjugates from your weak acids, right? So if we think back to this figure here, right, we had all of these weak acids, right? Now, if these are weak acids, their conjugates are all weak bases. Yes, does that make sense? When we're assessing our weak bases beyond amines are going to be the conjugates of our weak acids, yes? All right, going back to where we were. So, thinking about our K expressions and making sure we can write those, we have our CH3NH2, right? And if we were going to do the hydrolysis of that in water, we would use our double arrow there. Now, since these are bases, they are proton acceptors. So now we just need to think about this, right? So, again, our structures tend to be written in a way that expresses what's attached to what, right? So here, this CH3 is a methyl group, right? So one carbon attached to this nitrogen. These two hydrogens are attached to that nitrogen, right? So what we have is a nitrogen, hydrogen, hydrogen, and then a CH3 group, right? Which means that there's that lone pair there, right? Which is why it functions as a weak base. So always envision that structure of ammonia, and that's going to help guide what your weak bases, your weak base amines look like, okay? So then, anyway, with this water, what that means is now we have CH3NH3, and by adding that H on, we've now turned it into a cation, plus that hydroxide, which is what makes it basic, yes? Now, if we take that, we can write a Kb expression that says CH3NH3 plus and our OH over our initial base, because again, just like we said previously, right, that water doesn't count. All right, and then likewise, we could do it for a, this is a more traditional, coming from a weak acid, right? So we have this. And now, again, just like we've talked about before, it's just going to become singly protonated, okay? We're not going to double do it in one fell swoop, right? So we'd have that plus our hydroxide ion, right? And we could write a K expression for that. Now note, right, because this is the conjugate from a weak acid, right, there are a lot of ways we can approach it, right? And what we're going to talk about, and assuming you've already finished your unit, right, in 16.8, we tie together the concept of our Ka and our Kb by tying it to Kw, right? Which means that all of this is interrelated, which means really every problem we've done so far could be solved either from a base perspective or from an acid perspective. So it's going to be really important that as we solve these problems from here and through the rest of the chapter, you look at both perspectives, and for most people it's going to be helpful to figure out which one makes most sense to you, and then you would just always take that route. You know, for some people, obviously, like switching back and forth doesn't matter, right? But that's something to be thoughtful about as we assess the next few problems. So, what is the molarity of aqueous NH3 that has a pH of this? So let's talk about what information we know. So first of all, we know we have a pH of 11.17, which really means, right, we have an H3O plus of 6.76 times 10 to the negative 12 molar, right? Which means that we also have a hydroxide ion concentration of this, right? Tying those pieces together, right? And so here, what are we missing? Right, we're missing a K, because all this is going to have to get tied into a K. So first, let's go ahead and just write out what's happening. So we know that if we have ammonia in water, right, hopefully we would stop and assess, oh, ammonia is a weak base. It's got a lone pair. It's going to accept a proton and give us ammonium plus hydroxide ion, right? Which means that we can then write a Kb expression for this, which would say NH4 plus times OH minus gives us our NH3, right? And then you'd say, ooh, we're missing a KB. Well, we know that because we would use our resources from the book, and that's our KB value, which then means the problem's relatively simple, right? We're going to take 1.8 times 10 to the negative fifth is equal to, right? And we're going to take this, and this is also the concentration of NH4 plus, right? Does that make sense? Because all of it comes from the dissociation of NH3, right? So we actually have 0.0015 squared on top of, right? And here, right, is that, right? And again, if we want, we could write out a rice table for this. I don't know why I keep putting this underneath here and then I have to move it. So if we wanted to do our rice table, we could just put in our pieces, right? Which say that if this is x, right, and this is 0, 0, right? And we know that eventually we end up with 0.0015, right? 0.0015. Then this must be minus 0.0015, right? Does that make sense? Which is how we get our numbers for here. And then we'd solve for our x. Yes, does that make sense? All right, fantastic. Next up, oh, that's it. All right, thank you for listening. Be good, and I will see you soon. And next up, let's tie together